Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O-Levels Physics 5054. Today we have set our hearts to solve a theory paper. We call it paper 2, and for this purpose we have selected May-June 2010 2 paper. This paper 2 belongs from the Zone 2. In this video, I'm going to attempt the section B of this paper. Section A of this paper I have already solved, and I have made a video on it, and it has been uploaded in my YouTube channel. In this video, we are going to only attempt the section B of this paper. Both these sections will be in the same playlist. So let's start. And okay, so the section B of this paper is showing up on your screen. Question number 9. Figure 9.1 shows a car braking on a road and coming to rest. Explain what is meant by the thinking distance. You see, thinking distance means that when you see an obstacle on the road, when you see an obstacle on a road and your brain processes that there is some obstacle on the road, and your foot goes to the brake pedal. So this is called reaction time, and in the reaction time, the distance traveled by the vehicle is known as the thinking distance. So here we go. The thinking distance. Thinking distance is the distance traveled while thinking and before applying the brakes. Or you can say the distance traveled while thinking, or the distance traveled in the reaction time before the braking starts. Yeah. Then we have the braking distance. And braking distance is the distance which the vehicle will travel after you have applied the brakes. So after application of the brakes, the car will travel, after the application of the brakes, the car will travel some distance before the car comes to rest. That is known as the braking distance. So distance traveled while braking until the car stops. Distance traveled while brakes are applied, the car decelerates. Okay, an engineer conducts a test on the car and finds that the braking distance is greater when the car is fully loaded than when it is unloaded. Apart from the road condition state, what must be kept the same in the test? If you are testing how much is the braking distance, the one thing you should keep same is the speed of the car. Okay, it depends upon the speed of the car that how much the braking distance will be. So I think the speed of the car, here my student has written the same types of tires. There are the many factors, and one of them is the speed of the car, and one can be the same types of tire on both the cars. Speed of the cars or same force pressure on pedal, or same braking force, or same tires or conditions of the brakes. Explain why the car has a greater braking distance when fully loaded. You see, when the car is fully loaded, it has larger mass, so it has larger inertia. So when the mass is larger, so you will you give it the same resistive force, then it will have less deceleration in it. So now the car will cover larger distance before coming to rest. More the mass, less will be the deceleration if the same frictional force is applied. So the car will have cover larger distance before coming to rest. Fully loaded car have greater inertia, so it decelerates slowly. The amount of deceleration will be less. So now the car will travel larger distance. Greater inertia, kinetic energy, momentum, or smaller deceleration or acceleration? So our answer is right. Then we have state and explain how one road condition affects the braking distance of the car. Use ideas about friction in your answer. For example, if the road is wet, then the friction between the tires and the roads that will decrease when the road is wet. For example, it's raining, then there will be water on the road, and due to that, what will happen? The friction between the tire and the road will decrease. Now the braking distance will become larger because the friction between the tire and the road will decrease. And if it is dry, it means the road is dry, there is no water on it, or any kind of lubricant on the road, for example, oil leakage. When there is no, the road is totally dry, then the friction between the tire and the road is larger, and the braking distance becomes smaller. When the road is wet, friction between tire and road is less, so the braking distance is greater. C part. Any road condition, for example, icy, wet, poor surface, slippery, smooth, rough surface, and its correct effect on distance. Correct explanation that refers to friction, for example, more friction when dry. Okay, so then we have explain how wider tires affects the pressure of the car on the surface of the road. If the tires are wider, so their contact area with the ground will become larger, and you know, when the contact area is larger with the road, the weight of the car is still the same, so the pressure will become less. If the contact area with the ground is larger and the weight of the car still the same, then the pressure will become less. As more area of the tire is in contact with the road, so the pressure decreases. Pressure is force divided by area. That was the D part. Okay, then we have the car has a total mass of 900 kg and is traveling at 20 meter per second. At time t equals to 0, the driver sees an accident ahead. He applies the brakes at t equals to 0.60 second to stop the car. After the brakes are applied, the car comes to rest in a further 4 seconds. Calculate the deceleration of the car as it brakes. So the deceleration is initial speed is 20 meter per second. The final speed will be 0, and this happened in 4 seconds. So I can calculate the deceleration. Deceleration is the change in the velocity. Change in the velocity divided by time. Here the change in the velocity is from 20, the speed went to 0, and this happened in 4 seconds. So 20 divided by 4, and that will be 5 meter per second square. And it will be negative. So because we are saying it's deceleration in your final answer, you will not put the negative sign because you are saying deceleration. So E part, this was the E part. So our answer is right. Okay, then they say calculate the braking force acting on the car. The braking force will be F equals to MA. F equals to MA. F, we want to find out. M is the mass of the car. A is the deceleration we just calculated. So we can, F is equals to MA, 900 kg is the mass of the car, and into 5, that is 4,500 Newton. So the force is 4,500 Newton. Okay, then we have on the figure 9.2, draw speed time graph for the car as it brakes. Okay, so we know the deceleration and we know the duration also. Okay, let me show you. For 0 points from 0 to 0.6 seconds, you know, this is 0.6 seconds. The car continues with this speed of 20. And at 0.6 seconds, they applied the brakes and it goes further 4 seconds and come to rest. So from 0.4 second, if you add the 4 seconds, it will become 4.6 seconds. So here it will come to rest, this point. This is 4.6. So from here, join here, draw straight line. Why? Because the car is decelerating with the uniform deceleration. I hope you understand. Here we have speed, here we have time. Okay, so that's right. Then we have state how your graph in the third part can be used to find the total distance traveled by the car. The total distance traveled by the car is the area under the speed time graph. Area under the speed time graph is the distance traveled. Okay, area under the speed time graph. So this is how you do question number 9. So we are now on question number 10. Describe a method for measuring the speed of sound in air in your account. State clearly how the sound is made, what measurements are taken, how the result is calculated. One precaution to produce an accurate result. So method is very simple. We will go into a ground and we will take two parties. One will be on the point A, the other party will be on the point B. The distance between them should be like 1,000 meters. And this ground should be flat. They should be able to see each other. And this party A, they will have a flash gun. Okay. They will fire a flash. This party will have a stopwatch. Okay. When the party B sees the flash, they start the stopwatch. And when they hear the bang of the sound, they will stop the stopwatch. So now they have the time the sound took from traveling from A to B. And with the help of a measuring tape or with the help of a trundle wheel, they can tell the distance between A and B. They can divide the distance between A and B with the time taken. And that will give them the speed of the, the sound. And then what they can do, that they can switch their roles. For example, now the party B will use the flash gun and the party A will use the stopwatch. Okay. They will fire the flash gun. When the party A will see the flash, they will start the stopwatch. And when they will hear the bang of the sound, they will stop the stopwatch. The distance between B and A, they divide that distance with the time they get on the stopwatch. And by this way, they can calculate the speed. Then they can take the average of the speed. By doing so, you will be able to correct if there is any error due to the wind. Okay, so this is how we, it's a 5 marks question. I hope you understand. Let me show you what Aisha has written. Okay. A student stands few meters. Instead of saying few meters, we can say 1000 meters. The distance should be large enough. Okay. A student stands 100,000 meters away from the other student. Measure the distance between the two students using a trundle wheel. One student fires a gun. Other student, when sees the flash from the gun and during the burst, starts the stopwatch. When he hears the sound, he stops the stopwatch. Speed of the sound is calculated by the distance traveled by the sound and the time taken for the sound to travel. Repeat the experiment. Speed of sound is calculated by, here we should say dividing, by dividing the distance traveled by the sound and the time by the time taken for the sound to travel that distance. Repeat the experiment and take average mean so that the result can be more reliable. Okay. So here you see in this answer, she has not mentioned the change. For example, once the A party, they will fire the flash gun and the B will time the sound, and then the B will fire the flash gun and the A will note down the time. So also mention that here. Okay. Hopefully you understand. Here we have how sound is made. For example, gun, clap, hands, hit metal. Correct measurement of time. For example, from seeing flash to hearing sound, or clap, echo. Correct measurement of distance. For example, gun to observer, observer to wall. Correct calculation for measurement. And precautions, for example, time, clap, or echo, and time 10. Ensure no wind. Repeat in opposite direction. Repeat and average. Use large distance. Use more than 200 meters. Okay. So I hope you will be able to write this answer. Okay, then we have ultrasound is used in quality control to detect cracks in metal. Pulses of ultrasound are sent into the metal from a transmitter. A detector is placed next to the transmitter on the front surface of the metal. Figure 10.1 shows the oscilloscope trace of the ultrasound pulses produced if the metal contains no cracks. Okay, so if there are no cracks, this is the main pulse you have sent, and this is the reflected, the echo, main pulse, reflected, main pulse, reflected, main pulse, reflected. Each division here represents 10 expo minus 6 seconds. 10 expo minus 6 seconds. One division along the x-axis represents 1 expo minus 6 seconds. Pulses labeled S are the pulses initially sent out from the transmitter. Each pulse labeled R is the reflection from the back surface of the metal of the previous pulses S. State what is meant by ultrasound. Ultrasounds are sound waves whose frequency is more than 20,000 hertz. Okay, so they are out of the audible frequency range. Their frequency is more than the audible frequency range. Ultrasound is a sound wave with frequency greater than 20,000 hertz. Here you can see this. Answer is right. He said use figure 10.1 to calculate the number of pulses sent out by the source in 1 second. So from this diagram, I can tell you the time period of the pulse. 1, 2, 3, 4, 5, 6. So after 6 multiply 1 expo minus 6 seconds, the pulse is sent. The time, so now I know the time period. Once you know the time period, you can calculate the frequency. So it is the one pulse sent out in 6 into 10 raised to power minus 6 into 1 into 10 raised to power minus 6. So that is 6 expo minus 6 seconds. That's the time period of the pulse. And the number of pulses will be in 1 second, that is called frequency. And the frequency will be, 1 by f. 1 by, sorry, f is equal to 1 by t. I said 1 by f. F is equal to 1 by t. So 1 divided by 6 expo minus 6, and that will be 16667, which is approximately 1.7 expo 5 pulses. 1.7 expo 5 pulses, and that is the frequency. Then their question is, so just two reasons why the amplitude of the R is less than the amplitude of the S. You can see the amplitude of the, let me show you. The amplitude of the actual wave, the pulse is larger. The amplitude of the reflected or the echo is smaller. The reason is simple, because the echo, the reflected sound wave or the ultrasound has less energy in it. Some of its energy has lost, maybe absorbed by that body from where it is reflected. Some energy of the sound is absorbed by the metal. Not all sound is reflected backward. Another reason is that not all the sound is reflected back. Okay. Some sound travels further. Okay. Where is that? Yeah. Not all sound is reflected from back surface, or some passes through the back. Some energy sound absorbed by the metal. Sound energy spreads out, scattered, reflected in another direction, dispersed, travels a greater distance. Okay. Sometime later, the piece of metal is tested again. It now has a small crack halfway between the front surface and the back surface. And figure 10.1, draw the position and size of the pulses produced by this crack. Label each of these pulses C. Okay. So now you see, here you see, this is C. Because the sound is reflected back whenever there is a change in the density of that metal. So from that boundary, the pulse is reflected back. And so now, because you have the crack exactly halfway between the front side and the back side of the metal, so we think that the C will come between S and R, in the middle of S and R. And I think its amplitude will be larger than the R, but less than the S. Okay? What they say. At least one pulse halfway between S and R in the long gap. Total height of the pulse smaller than S, and 3 or more drawn and labeled C. Okay. So we are good with this. Okay. Then we have, he says, a second beam of ultrasound has a frequency of 8 expo 6 hertz and a speed of 4,000 meter per second in the metal. Calculate the wavelength of this ultrasound in the metal. You know, V is equals to F and lambda. Okay. V is equals to F lambda. So if you want to find out the lambda, it will be V divided by F. Okay, so V is equals to F lambda, and the V is 4,000 and F is 8 expo 6, and lambda is question. So lambda will be 4,000 divided by 8 expo 6, and your answer will be 5 expo minus 4 meter. 5 expo minus 4 meter is the right answer, sir. Okay, so we are going to next question. The next question here is question number 11. He says, describe an experiment, including an ammeter and a voltmeter to show how the resistance of a wire varies with temperature. Draw a circuit diagram. So let me show you, we have done this. So here you can see we have a battery. Here we have connected it with the wire, and this has been connected back. This is the ammeter, this is the voltmeter, this is that wire. And here we have water in it. So there we have water. This is water basically. And here we have a thermometer with it. Okay. So what I will do, I will pour hot water, and suppose the temperature of the water from thermometer I know is 80. And suppose I want to do this reading when the temperature is suppose 70. So I will wait. When the temperature will become 70, I will close the circuit. I have not shown here a switch. So let's see, for example, here we have a switch also. So this is a switch also there. So when the temperature will become 70, I will close the switch. When I will close the switch, what will happen? Immediately note down what is the reading on the ammeter, what is the reading on the voltmeter. Just note down them and open the switch. You can divide the voltmeter reading with the ammeter reading, and that will give you the resistance of the wire. And then wait. Now, when the temperature becomes, for example, 60, this is for example, because the temperature will be automatically dropping, and you are noting, you are keeping an eye on the temperature by looking at the thermometer. So when the temperature becomes 60, suppose, again close the switch, note down the readings on the ammeter and the voltmeter. And after noting them, immediately open the switch. And then wait. When the temperature becomes 50, again close the switch, note down the reading on the ammeter and the voltmeter, and open the switch. In this way, on different temperatures, you will be able to calculate the voltage and drop and the current through the circuit, and you can at the end calculate the resistance of the wire in that temperature. Okay. So place the wire in the beaker with the hot water of temperature of 80 degree. Switch on the circuit and note the readings of ammeter and voltmeter. Switch the circuit off when temperature of water decreases to 70 degree. Thermometer in the water beaker tells the temperature. Again, switch the circuit on and measure the reading. Calculate the resistance. Now you will have repeat experiment with different temperature, for example, 60, 50, or 40. Calculate the resistance by dividing the voltage and current. Plot a graph of the resistance against temperature. Okay, so this is our answer. Let me show you how it can be. Now I think you can see the whole question. What the marking scheme says, it says circuit diagram with cell and ammeter in series with resistor, wire, lamp, and voltmeter across resistor. R is equal to V by I in any form or gradient of V. I graph, thermometer, thermocouple used or shown, statement of how different temperatures obtained, for example, water bath, oven, heat, room change, supply voltage or current or series resistors to change temperature. Okay. Then, the filament in a lamp is made from metal wire. Describe the variation with temperature of the resistance of the filament lamp. You see, when the temperature of the filament lamp becomes higher, the resistance of the filament lamp also increases. And when the temperature decreases, the resistance of the filament lamp decreases. Okay. Resistance has a proportional relation with the temperature. As the temperature increases, resistance also increases. Okay. So that is our answer. You can see the answer. Then we have, he says, on the figure 11.1, sketch a graph of the variation of the current in the filament against the potential difference across it. You see, because the current is here, and now the gradient will be equals to 1 by r. So as the gradient here will decrease, it means the resistance will decrease. Here the gradient here, the slope here of this graph will be equals to, I by V, and that will be basically 1 by R. Okay. So this should be like this. Okay. Because as gradually the gradient will decrease, that will mean that the resistance is increasing. Okay. So the graph should be like something like this. And I have told you the reason. The reason is this. As the slope is gradually decreasing, that means the resistance is gradually increasing. Okay. Then we have question C part of this 11 question. Figure 11.2 is a circuit used to monitor changes in the room temperature. A thermistor is connected in series with a 6-volt battery and a 2000 ohm resistor. The temperature of the room increases. State and explain what happens to the reading on the ammeter. As the temperature will increase, the resistance of thermistor will decrease. And as its resistance will decrease, so the total resistance of the circuit will become less. So the current from the battery will increase, so the reading on the ammeter will increase. Again, when the temperature will increase, the resistance of the thermistor will decrease, so the total resistance of the circuit will become less. So now a larger current will come out of this battery, and so the ammeter reading will increase. It's a 2 marks question. Let me show you. When the temperature increases, resistance decreases and more current flows in circuit, so the ammeter reading increases. Okay. Then it says the reading on the voltmeter. Okay, the reading on the voltmeter. Okay, they want me to find out the reading. You see, as its resistance will become less and larger current is flowing. Now think about this. Its resistance has not changed, but the amount of the current which is flowing through this fixed resistor, that has increased. Its resistance is constant, but the current flowing through it has increased. So V is equals to IR. So R is constant, but the I has increased. So the voltage drop across this resistor will increase. So the reading on the voltmeter will increase. I hope you understand this. Greater current flows through the fixed resistor, so potential drop against it increases. Voltmeter reading increases. Yes, that's true. Okay. He says at a certain temperature, the reading on the voltmeter is 3.8 volt. Calculate the resistance of the thermistor at this temperature. Okay. So 3.8 volt. The reading here is how much? They are saying 3.8 volt. If the reading is 3.8 volt, I know the resistance. I can calculate how much is the current. Same current will be flowing through the thermistor. From here, the EMF is 6 volt. If this is taking 3.8, So this will be taking 2.2 volt. So if I know the voltage drop here, I know the current here, then I can calculate the resistance of the thermistor also. This is the strategy. So let me show you. First of all, we will calculate how much is the current flowing through the fixed resistor. I is equals to V by I, 3.8 divided by 2000, and that will be 1.9 expo minus 3 ampere. And because the thermistor and that fixed resistor, they are connected in series, the EMF of the battery is 6 volt, the voltage drop on the fixed resistor is 3.8 volt. So the voltage drop on the thermistor will be 6 minus 3.8, that will be 2.2 volt. Resistance of the thermistor is the voltage drop across the thermistor is 2.2. The current flowing through, because they were connected in series, is same as the current flowing through the fixed resistor. So the 2.2 divided by 1.9 expo minus 3, and that will be 1157.8, which is approximately 1160 ohm. 1160 ohm. Okay. That's right answer, sir. So, my dear students, we have reached the end of this paper. This paper is over. Now we have blank pages. Let me show you. Okay, the paper is over. So, my dear students, today we have done May, June 2010 2 paper. It's section B. In this video, we have solved its question number 9, question number 10, and question number 11. That was the section B. And the section A I have done in another video. Both of these videos you will find in the same playlist on my YouTube channel. If you think that this video is helpful, it has helped you, please share the link of this video with your class fellows, with your junior students, with your senior students, with your teacher. When you do this, this helps me to promote my channel. And one thing is very important, that it's possible that I can make a mistake. And sometimes this happens, that we make a mistake. We are human. That's why we say it should be your habit that you should always check the answer with the marking scheme, or you should consult it with your own teacher also if you find something weird, because it's possible that we can make a mistake. Okay, so thank you very much for watching this video. And I think it's a great blessing for me that I can make these videos and I can touch the life of so many students around the globe. Thank you very much. Have a good day. God bless you all.